Hello, everyone. This is Charleston here, and I would like to thank the organizing committee for inviting me to give this keynote presentation. And the title of my presentation is Unsaturated Soil Mechanics and Bioengineering Slopes, with a focus on hydrological effects. Before I continue, I would like to thank my co-authors, Dr. Lin Jinjun and Dr. Zhou Chao, for their significant contribution of this keynote paper. Actually, Sri Lanka is not that far away from Hong Kong. And you can see in this map here, and actually within the two different time zones only. I'm from Hong Kong, and Hong Kong is located at the south coast of China, and here's Sri Lanka, which is quite close to Hong Kong. When you go to Hong Kong and you land at this airport, you travel to the east, okay, and you reach the my university, Hong Kong University of Science and Technology. Before you reach our campus, you may reach this beautiful Victoria Harbour. By the time you reach our campus, which is normally takes about 45 minutes by car to reach my campus, and here's just a couple of pictures showing our campus. And my university is exactly 30 years old. It was established in 1991. We have 4 major schools, about 10,000 undergraduate students, and 5,500 postgraduate students, including 3,500 MSc students. And our geotechnical is pretty big, and we have about 60 PhDs and 30 MPhil students. Here, just a couple of more pictures showing our campus. I hope you do agree with me. Our campus is very, very beautiful, and it's located on the hillside and facing the sea. If you look at the bottom left of the picture, and there are a couple of, those are the buildings and facing the sea. But one particular building I'd like to draw your attention is this one here, which is housed our geotechnical centrifuge. And our geotechnical centrifuge is one of the most advanced geotechnical centrifuge in the world, because it's equipped the world first by also shaking table on the left-hand side, you can see here, and also it is equipped with a 4-axis robotic simulator. And that means we can control construction activities while the centrifuge is spinning. And although our university is relatively young, but is highly recognized. Okay, according to Times Higher Education, among the young universities, in last year we ranked #1 in the world. And again, for the young university category, ranked by QS, actually we ranked #2 in the world this year by QS. And our Financial Times Global EMBA ranking last year #1 in the world, and Global University and Portability ranking, and in 2019, #10 in the world. Okay. One piece of exciting news I'd like to report to you is we are building a new campus in Guangzhou, which is only 27 minutes from Hong Kong to Guangzhou. If you catch a right train from Kowloon West and traveling towards the northwest direction, and 27 minutes later, you reach our Qingsheng station. And that's where our campus is located. And the size of the campus in Guangzhou is double the size of the Hong Kong campus. And English will be the official language of instruction. Here are a couple of views of our campus. And the campus is scheduled to be opened in September 2022. Actually, it's less than 1 year away from now. And in the new campus, we will have 6,000 postgraduate students and 4,000 undergraduate students. Here are a couple more views of our campus. We are actively recruiting 400 academics and 4,000 postgraduate students now. we do provide different types of scholarship for students. For example, exchange scholarship, each student will receive about $1,200 per month. Our scholarship for full-time students range between 2,100 to 3,500 per month. Now remember, this is per month, okay? And also with our dual degree programs. What does that mean? Dual degree program between Hong Kong campus and Guangzhou campus. So in other words, a student can stay 2 years in Guangzhou and 2 years in Hong Kong and get a dual degree. This is a picture showing a typical time of my research group. And I have research students, research assistant professors, and postdocs from different countries. And one student I think you should know is Rohingya De Silva. She received a Hong Kong PhD fellowship, and her scholarship is over $3,500 per month. I do like to encourage any students and in the audience, or you know any bright student would like to study in Hong Kong, then please let me know. Now let's move on to the technical contents of my presentation. Firstly, I would like to give you a background of our research, briefly introduce unsaturated soil mechanics relevant to vegetation. And I will report to you the relationships between plant characteristics and soil suction. Then I would like to report to you our centrifuge and numerical modeling of combined hydrological and mechanical effects on slope stability and failure mechanisms of different root architectures. And finally, I'd like to draw a conclusion. Now let's move on to the background of our research. These two pictures were taken when I was in Lebanon in 2017. Just outside the ballroom, and I could see these two slopes are very stable without any support. Why? If based on saturated soil mechanics, and these two unreinforced slopes should have failed. Let me show you some study on a highway slope in Australia. The objective of the study was to study the influence of different grass type on surface erosion and stability of the slope along the highway. And after 40 mm rainfall in 10 days, and if according to Hong Kong, that would be equivalent to 2 year return period. What you can see here is the slope at different sections behave very differently, depends on what type of grass were planted. So this clearly illustrates the plant types have a significant effect on surface erosion and slope stability. Now let's move on to a bit of introduction on unsaturated soil mechanics relevant to vegetation. And I'm sure you all know sandcastle. And we played sandcastle when we were young, and typically you will find, whether in the lab or on the beach, typically you will find on the beach, if sand is dry, then you cannot form a castle. On the other hand, if you put sand underwater, you will not be able to form a sandcastle. But if you use moist sand, then you will be able to form a sandcastle like this. And obviously, on the left-hand side is dry, and typically in our undergraduate textbook, we assume suction is 0. And obviously, this is wrong. Okay. And on the right-hand side here, when sand is submerged underwater, then the suction is 0. In the middle, that's where this sandcastle stands out. Obviously, it's because the presence of suction. According to thermodynamics, total suction can be defined by this expression here. This slide looks very heavy, but don't worry. Okay, I would like just to highlight some key components of this equation. Now, so total suction can be expressed by this thermodynamic equation here, and in particular, is related to relative humidity in the soil pore. And this part can be separate into, actually this part actually consists of two components. The first component is matrix suction, and the second component is osmotic suction. But in most of geotechnical problems, osmotic suction, the second component is osmotic suction due to the change of concentration of solution in the soil pore. And normally this component is ignored in our geotechnical field. So in other words, we only have to consider matrix suction. Okay, this component, matrix suction here. And matrix suction is defined as UA minus UW. Pore air pressure minus pore pressure is called matrix suction, and we give a symbol S. And if you recall, the dry sand case I showed you in the previous slide, actually dry sand has a very, very high relative humidity. That means it has an infinite high suction, but sandcastle cannot be formed. Why? That's a very interesting question, isn't it? Okay, infinite suction, but sandcastle cannot be formed. But in the middle one, if you recall, okay, let me go back. Okay, in the middle one, with moderate suction, then the sandcastle can stand happily. And on the right side, of course, suction is 0, then the sandcastle collapse under water. But the key question is why dry sand cannot form a sandcastle, even though it has a very, very high suction. This is because there's no enough meniscus water in this dry sandcastle to, if I may explain this loosely, there's no enough meniscus water to bond the sand particles together. That's why dry sand collapses, even though it has a very, very high suction. Now let me introduce to you some simplified failure criteria for unsaturated soils. This equation is more Coulomb failure criteria for saturated soil. I guess everybody is very familiar with this equation. And how about for unsaturated soil? Then Bishop in 1959 proposed an equivalent more Coulomb failure criteria for unsaturated soils. Nowadays we call Bishop's equation. And again, he retains the effective cohesion, but modified the second component of the more Coulomb equation into two parts. Okay. And the first part is due to the confining stress. Okay. Total stress minus UA, okay, is confining stress. UA, remember, is pore air pressure. And the second component is matrix suction component, UA minus UW, with a correction factor, chi. Okay. Subsequently, researchers like Napoli further revise this Bishop's equation, given out here. The first component is the contribution from effective cohesion. The second contribution is come from net stress and effective friction angle. The third component is contributed by mixture suction and together with its water content in the soil. But all simplified failure criteria for unsaturated soil suffer similar problems. What are the similar problems? For some not true for entire range of degree of saturation. In other words, cannot explain the collapse of a dry sandcastle. Not considering effects of suction-induced dilatancy, and also not consider the effects of wetting and drying cycles and freezing and flowing cycles. Now let's move on to water flow in unsaturated soils. And similar to saturated soil mechanics, water flow in unsaturated soil governed by the same Darcy's law, and which I'm sure you all know is V equal to minus Ki. Okay, V is the velocity water flow, and Kw is what we call permeability. Okay, in a simple way, and I is the hydraulic gradient. In a saturated soil mechanics as well, then permeability typically is a constant number. Of course, we know that it varies with variation, but most of the time we consider variation doesn't change. Okay. Of course, this is our assumption. Okay, it's not true, but it's good enough for engineering purpose, at least. Now, but for unsaturated soil, life is not that simple because the Kw is not a constant anymore. Okay, actually it varies substantially according to suction or according to degree of saturation. Okay. And this is illustrated here on the right-hand side diagram. And what you're seeing is permeability versus suction. So when suction equals 0, then we all know that permeability of sand is much higher than silt, okay, and which in turn is much higher than clay. But if you look at this graph, the permeability is not constant at all when suction increase. You can see sand permeability of sand drops significantly as suction increase. But on the other hand, clay, the permeability of clay also decrease as suction increase, but in a much gentle manner. So clearly we cannot use Kw as a constant anymore in unsaturated soil. So in an unsaturated soil world, we use so-called permeability function. So permeability of unsaturated soil, Kw, can be expressed by a function of E and SR. And when the soil is fully saturated, then SR equal to 1. That's why in our saturated soil world, then Kw is only a function of Y ratio. But in an unsaturated soil world, then degree of saturation play a major role affecting the permeability of an unsaturated soil. How about the effects of plants? Plants, just like human beings, have to drink water. So plants will suck water from the soil to the plant, increase suction, and hence reduce water content in the soil. By doing so, the effects on the soil will be reduces permeability, which is good for engineering purpose. That means reduce rainfall infiltration. The reduction of permeability with an increase of suction or reduce of water content can be illustrated by this simple illustrative diagram here. On the left-hand side is a low suction zone with, in other words, high water content. If you remember the hydrodynamic equation. And water, we find an easy short path flow through the soil like this, shown by this black line. If we increase suction, and that means reduce water content, then the water flow from the top to the bottom have to find a more tortuous path shown by the red dotted line here. When suction is very high, and that means the water content in the soil is very low, illustrated on the right-hand side diagram here. And water could not find its path flow through from the top to the bottom. So with this simple illustration, clearly shows that the permeability of an unsaturated soil is highly depending on the degree of saturation in the soil. We cannot assume permeability is a constant anymore. Right, so let me give you a quick summary of the effects of vegetation on soil behavior and hence on slope stability. So point number one I'd like to make is certainly plants will increase shear strength of the soil because of this term here. This term is matrix suction. If matrix suction is not equal to 0, then there will be an increase of shear strength. That's why sandcastle can stand up when we give us suitable water content. The second effect of vegetation on unsaturated soil is affecting its permeability. So in other words, the permeability is not constant or almost constant anymore. Actually, it highly depends on degree of saturation, or in other words, highly depends on suction. And because the plants affect the water content in the soil, then it certainly, then when water suck water from the soil will reduce the permeability of the soil itself. Here just show you some of our tests to illustrate the effects of different plants on an unsaturated soil. On the left-hand soil column here is a bare soil, no vegetation. In the middle is a soil column planted with shrubs. On the right soil column is planted with grass. And we before we add water to these three soil columns, and we allow the plants to do their own work. Okay, that means sub water. Okay, and it's at their own pace, or wherever they like. Okay, from the soil. Then we apply water on top. Means we create a ponding condition for 48 hours. That would be equivalent to a rainfall more than 1,000 year return period in Hong Kong. So then let's see what happens. Okay, let's see. So here just shows the results before and after our ponding test on the three soil column. And let me take out my laser pointer. And the black line here shows the distribution of suction along the depth of the soil column. The red line shows the distribution of measured matrix suction within the soil column planted with grass. So what you can see here, there's a 70% of increase of suction as compared with the bare column. The blue shows the measured distribution of suction in the soil column planted with strobes. There's another 25% increase of soil suction in the soil column planted with strobes. Then what happens after ponding? The suction within the bare column almost destroys. That means suction equals 0 up to about 0.8 meter depth. Similarly, the soil suction vegetated with grass and suction got also reduced to 0 and up to 0.6 meter deep. But further down there, some suction retained. And how about the soil column planted with strobes? This is shown by this blue dotted line here. And what you can see, actually, the pretty high suction still remain in the most parts of the soil column. So what does that mean? Remember, the three soil columns were subject to 48 hours of ponding. And for this soil column vegetated with strobes, quite substantial high suction can still remain. This is quite remarkable. So based on this three soil column tests, clearly illustrate that vegetation plays a significant role on the suction distribution in the soil. If you're interested what I just explained to you, then you're welcome to take a look of my book published in 2007, which is quite old, but still is relevant. And the title of the book is Advanced Unsaturated Soil Mechanics and Engineering. So let's move on to hydromechanical effects of plants' roots on slope stability and failure mechanisms. Just a little background, and there's a couple of pictures showing failures at various places in China, including Hong Kong on the top left, Wenchun, Shenzhen, and Chongqing, etc. So how can we improve slope stability, and how can we do the rehabilitation? Greening is our major objective of our research. This is a schematic diagram to illustrate our ideas. Can we use plants as a natural engineer to stabilize the slope? Using the plant root as a mechanical reinforcement has been used or reported for years. But if you understand unsaturated soil mechanics, then you should know a plant can do more than just mechanical effects. Actually, plants can contribute significantly to the soil suction in the ground. That means enhance shear strength of the soil. Also, plants can reduce permeability of the soil, hence minimize rainfall infiltration. So with these two positive effects on slope stability, and I describe them as a hydrological effect in addition to traditional mechanical effects. So now let's move on to experimental test cell and plant species tested. But due to in the interest of time, I will only go through this very briefly without going into details. In order to study the effects of plants, we use different types of indexes to suit different needs. The first one I'd like to introduce is so-called LAI, leaf area index. It's the sum of the leaves divided by the area of our concern, AC. The second index I'd like to introduce to you is RAR, root area ratio. Okay, and illustrated by this figure here is the cross-section area of the roots divided by this area AS. The third one is root area index, which is defined as the surface area of the roots divided by the area AS. Fourth one I'd like to introduce is root volume ratio, is the volume of the roots divided by this volume of the soil, VS. Regarding engine application of the plant indices, so I would say leaf area index LI can be used to quantify solar radiation intercept by leaves, and also can quantify effects of soil suction, etc. And RAR, root area ratio, can study the effects of roots on the soil shear strength. And RAI, root area index, can be considered to quantify the effects of root water uptake, poor resistance, etc. Root volume ratio, we can consider to use to study the effects of root volume and soil water retention relationship, and also the tensile strength of the roots. In our university, we have different plant rooms, and just like to show you here. Okay, those are the two plant rooms we study the effects of plants on soil. And this is our field test site we call Eco Park. Okay, and here we have an area 6 meter by 10 meter to study the effects of different plants. And we have an embankment at the far end here, also for us to study the effects of plants on the soil. Here just the picture showing the study of the effects of different grass types on the soil suction. If you're interested in our work, then please go to take a look of the paper I list out here. For some, the first one is ecological engineering, Canadian geotechnical engineering, ecological engineer, published in 2016, and also 3 papers published in geotechnique. Here, just a schematic diagram show you how we study the effects of plants on soil suction. And this is just illustratively show a plant here, and actually within our lab, we can control the light wavelength and intensity. Of course, can control duration, and by doing so, then we can measure the suction distribution along the depth of this experimental setup. So based on our study, we can find the relationship between leaf area index and the increase of soil suction. And based on our study, we can find almost a linear relationship between the increase of suction and the leaf area index. On the right hand side, show you the relationship between the increase of suction with root area index, RAI. And the red line shows the measured suction after drying, and the blue line shows the relationship immediately after ponding of water. Once we know this type of characteristics, then perhaps, okay, we are still exploring. Then perhaps with this type of measurements, then we may be able to measure the leaf area index, say using UAV to deduce what's a probable suction increase in the ground. And also by knowing the root area index, then we can also figure out what is increase of soil suction in the ground. Let's move on to the results of field tests on the effects of plant roots on infiltration rate. So the tests were carried out on the embankment of the Eco Park, which I showed you earlier on. This picture shows double ring infiltration tests. On the left-hand diagram is a double ring device device that we use, but inside the two rings, grass were planted. On the right-hand diagram, shows a similar, actually identical double ring to the left-hand side, but this time the double rings were planted with Sulfura hyperphila, which is a shrub. Now let's take a look at the result. And what you're seeing here, infiltrated water volume on the first y-axis and the horizontal axis time. And the second column is the infiltration rate. So let's concentrate the amount of water infiltrate into the ground. The red line shows here is the amount of infiltrated water into the double ring with time. And this one is the bare one without any plants. But when this bare one compare with the double ring planted with tree and grass, you can see here there is a substantial reduction of water infiltration volume by 55% if the ground is vegetated by either grass or shrubs. So that experimental evidence clearly echo what I explained to you earlier on. Okay. The effects of plants can reduce water infiltration, and this clearly illustrated by this in situ and double ring infiltration test. Okay, now let's move on to centrifuge tests. Before I continue, I would like to recommend 3 papers for you to take a look if you are interested in what I'm going to say. And the first paper is 2017, published in Journal of Geotechnical and Environmental Engineering, ASE, 2016 in Landslides, and 2014 published in Geotechnic Letters. In our centrifuge, in order to simulate the effect of plants, actually we consider both hydrological and mechanical effects. Then we create model roots here and actually mimic reported root types in Hong Kong: taproot, hush, and plate. So those are our model roots to be used in the centrifuge test. Now, one uniqueness of our centrifuge test is we are able to create suction effects in the soil. Now, you compare previous reported centrifuge model tests, they only consider mechanical effects, but no hydrological effect, which I explained to you earlier on. Hydrological effect, in my mind, actually is very important, or even more important than the mechanical effect of the plant. If we only consider mechanical effect of plants, then why can't we just simply use soil nails, right? So I think we should pay more attention to the hydrological contribution of the plants to the slope stability. We develop our own model roots, which are capable to sustain suction, similar to those real plants in the field. So this is a typical centrifuge model setup and instrumentation. And this is test carried out in a complete decomposed granite, CDG, which is a silty sand, and the friction angle or critical state angle is 38 degrees. So this is a 45-degree slope. Within this slope, we install 15 of model plants in the slope. And when the tests were carried out at 15 G, so I mean 15 times the Earth gravity, and then we measure the infiltration rates, okay, and during the test. So here's a measurement of infiltration rates. The blue one is the result measured from the plates with tests, okay, and the red one is a taproot, and the green one is a heart-shaped root. And the dotted lines ones are the calculated ones, okay, based on numerical means. So you can see here the measured one and the calculated one, that means the theoretical one, certainly consistent with each other. What we can conclude from this 3 century tests is the infiltration rate certainly with the infiltration rate in the slope vegetated with plate wood is higher than the taproot than the heart-shaped wood. In other words, the heart-shaped wood has the most beneficial effect in terms of reducing the amount of infiltration. Here are just our measured results in our century test. For the taproot, for the heart shape, and for the plate root. Okay, during the test, but in the interest of time, I will not go in detail. But you're welcome to read our Keynote paper and also the paper I recommend to you early on. So now let me move on the effects of let's move on to the effects of wood architecture on slope stability. What you see here is federal safety plotting against different types of woods. Okay, the brown bar here represent the calculated result before year of transformation, and the red one here is after year of transformation, and the green line is after 8 hours of rainfall, which is equivalent to 8 hour rainfall of 70 mm per hour for 8 hours. That would be equivalent to 1,000 year return period in Hong Kong. So the purple one is the one represent there's no year of transformation, there is no plant. So as one would expect, if we consider the influence of plants due to year of transformation, then we will end up with a high fatal safety, okay, for all 3 different types of plants. Even after 8 hours of rainfall, shown by this green bars there. But on the other hand, if we ignore the effects of plants, then obviously the fatal safety drop below 1. So in other words, ignoring evapotranspiration effects can potentially underestimate fatal safety by up to 50%. Based on the 3 century tests at 15G, it clearly illustrates that the slope is stable at 45 degrees. Remember, the soil we use with a critical angle is 38 degrees. So in other words, in theory, the slope should fail after 1,000 year return period, but it didn't, purely because of the effect due to hydrological and mechanical effects of the plant wood. Actually, my student was very unhappy after carrying out 3 45-degree slope tests at 15G because no failure was observed. He could not study failure mechanism in a vegetated slope. Then I advised him to increase slope angle to 60 degrees to study the failure mechanism. So now let's investigate the effects of wood architecture on slope failure mechanism in 60-degree vegetative slopes. During the test at 15G, and the slope was subject to a rainfall intensity of 70 mm per hour in prototype, and the rain was last for 8 hours. That means equivalent to 1,000 year return period. Of course, this the quantity I just report to you are in prototype scale. And in each time, I will only show you a video on the test on taproot. So what you're seeing here is a 60-degree slope and subject to rainfall infiltration of equivalent to prototype of 70 mm per hour. Here, the rainfall nozzles allow us to impose rainfall on the slope during the century test in flight. So what you're seeing here is the continuing rainfall induced slope failure during the test. And those markers are used to deduce the displacement of the slopes. So when the rainfall continues, then you can see the substantial slope failure take place. Okay, so let's do a little bit more detailed investigation of the failure of the slope. So this is a 60-degree slope before rainfall. Those black markers were used to deduce the displacement field during the test. The right-hand picture shows a deformation of the slope after 1 hour rainfall, and this is after 2 hours rainfall that will be equivalent to 10-year return period. And this is on the right-hand side diagram is after 3 hours rainfall, and this 4 hours rainfall on the left, 5 hours rainfall on the right. The left-hand side shows the failure of the slope after 6 hours of rainfall, which is equivalent to 200-year return period. Photo on the right shows the slope after 8 hours of rainfall imposed on it, which is equivalent to 1,000-year return period. These two pictures compare the effect of fluid architecture on slope failure mechanism. On the left-hand side is the failure mechanism from the slope reinforced with taproot. And you can see here clearly a much deeper and also longer running distance of the failure. The right-hand side shows the slope failure of the slope reinforced by heart-shaped roots. What you can see here, compare the picture on the left-hand side, you can see this one has a much shallower failure mechanism. Now let's compare directly the running distance of the two slopes. On the left-hand side is the slope reinforced with a taproot. The running distance of the failure is about 4.7 meters in put-up scale, compared with the one slope reinforced with hardship roots is only 4.3 meters. Let's move on to the summary and conclusion. I hope you are convinced the hydrological effect of plants are substantial. The effect can increase the shear strength of soil and also reduce water permeability into the ground, which is substantial for slope stability problems. We developed a novel architectural wood model which can simulate both hydromechanical effect of plants with difference with architecture. This model roots enable us to study slope stability and slope failure mechanisms in centrifuge based on our physical tests and also numerical simulation today I don't have time to show you the numerical simulation. Our conclusion is that heart-shaped roots is the best. Actually, our research work provide scientific basis for environmentally friendly, sustainable development. This is our new book, which was published in 2019. What I have presented to you about the effects of plants on slopes, and you may find from this reference book here. Thank you for your listening. Have a nice day.